Beth.
And I'm Beth.
Welcome to Physics with Beth and Beth.
Hello everyone, and welcome back to Physics with Beth and Beth. I'm Beth, and in this video we're going to be continuing our journey through our calculus-based physics curriculum by diving into indefinite integrals. In our last video we talked about definite integrals, which are what we use when we want to find the area underneath the line, underneath a curve, between two specific points. But we also talked about how integrals are really antiderivatives. They let us rewind the clock back to our original function after we take a derivative. So what if instead of finding the value of that area between two specific points, I just wanted a general function? Well, there are a couple things that make that trickier, so we're going to be talking about those in this video today. So let's get started. Here I have a beautiful and definitely drawn perfectly to scale graph of two little functions. I've got x1 of t is equal to 3t cubed, and I have x2 of t is equal to 3t cubed plus 10. So just this guy shifted up a little bit. Now, just for funsies and for no deeper reason at all for sure, let's practice taking the derivative of these two things. This is something you guys have done a million times by now, so I'll zoom through it a little bit. The derivative of x2 of t, which would give me my velocity, would be, well, to take the derivative of 3t cubed, that gets me 9t squared. That 10, derivative of that is 0, so it's just 9t squared. And when I do the same for my blue function here, my velocity, 3t cubed, just gives me 9t squared as well. Well, that's interesting. Both of my original functions here have the same derivative, even though they're different functions, even though they're both offset by a different y-intercept here. They have a different, this guy has a plus 0 at the end, and this guy has a plus 10. But whenever we take the derivative, that difference goes away, and we end up at the same thing. Which makes sense. Where you start whenever you're running a race doesn't affect your velocity whenever you run that race, right? Your starting position and your velocity really don't affect each other that much, right? Or at all. So it should go away. Plus, that's how all the derivative rules that we've learned works. But that means whenever we take a derivative, we lose the information about that starting position, about our position at x equals 0, about that constant term that was here at the end of both of our original functions. So whenever we take antiderivatives, we have to keep that in mind. We have to remember that whenever you take a derivative, that constant term, regardless of what it was, becomes 0. So if we don't have extra information, we don't have a way of knowing in our original function if we had a constant term added at the end, and if we did, what its value was. Because whenever we took a derivative, that goes away. So let's work through an example where we see how to factor in that little piece of unknowledge that we have, that little thing that we don't know, and see how it plays out whenever we try to take an indefinite integral. Or another way of thinking about it is a general integral that's not defined strictly between 2 points, an expression as opposed to a value. Let's say I had a velocity graph, and that velocity graph with respect to time was equal to 3t squared. And I wanted an expression for the position of my thing that was moving with a velocity of 3t squared. So our goal is to find an x of t expression. Oh my goodness, that handwriting is terrible. Let's try that again. Is x of t is equal to question mark? Thankfully, we're also given another little piece of information in this problem. We're told that the position of our object, let's say my cat, because I love talking about my cat, she's adorable. Let's say this is my cat's velocity as she runs after cicadas in our backyard is 3 times the time squared. We're trying to find an expression for her position. Thankfully, we also have one other piece of information, that she is 6 meters away at time t equals 1 second. So we have this little piece of information as well. And we're trying to find an expression for x of t. Well, we know if velocity is the derivative of position, then position is the antiderivative of velocity. So let's just take an antiderivative or an integral. So x of t is going to be equal to the integral of velocity of time with respect to time. Notice here, unlike my last video, I'm doing dt. In our last video, we did dx. That difference is because t is what is represented on our x-axis. It's our independent variable here. So that's always what you put here at the end. That's the width of your rectangles on the x-axis, remember. Our expression for v of t, I'm going to just plug him in, is 3t squared dt. Another difference from my last video, I don't have a starting or ending value giving bounds to my integral. That's because we're taking an indefinite integral. We're trying to solve for a general expression for Juniper, my cat's position, at any time, as opposed to figuring out the distance that she traveled between 2 points in time. So this is what we've got. Now we have to think back about our antiderivative rules. To undo the power rule, what do? We add 1 to our exponent and divide by our new exponent. So we have, that's again terrible handwriting. We add 1 to our exponent and divide by that new exponent. So we end up with 3 divided by 3 times t cubed. But now we have to remember, whenever we take a derivative, we lose the information about our starting position, about that constant term that could have been at the end of our expression, at the end of our function. So I'm going to write in that that's a number that I don't know, that the expression for Juniper's position at any point in time is going to be equal to 3 divided by 3 times t cubed. I'm going to simplify that to just 1t cubed, plus some mystery number that would have gone away whenever we took the derivative to get to velocity. So now we're going to just solve for that mystery number. Thankfully, I can do that because I have an extra piece of information. If I didn't have this extra piece of information, I wouldn't be able to solve for that mystery constant term at the end. I wouldn't have enough information to be able to tease that value out. But we do, so we're going to solve for it. If you're ever working on a problem in class and you don't have that extra information, you stop here, and this is your answer. You say there's some constant term, I don't know what he is, he's C for constant. Thankfully we do know. I know that when t is equal to 1, x is equal to 6. So whenever t is equal to 1, x is equal to 6. So x is equal to 6 whenever I have 1 cubed plus c. 1 cubed is 1, so 6 is equal to 1 plus c, minus 1, c is equal to 5. So that means that whenever t equals 0 seconds, Juniper starts out 5 meters away. That's her starting position, my cat's starting position. So now I can just plug this in and we are all done. Let's pick that up. So then our position with respect to time would be equal to t cubed plus 5. And that would be a general expression for Juniper's position at any point in time if this was her velocity and this was her position at time t equals 1 seconds. All right, thank you guys for sticking with me through all of that. Indefinite integrals have that one extra step of complication beyond definite integrals. If you have any questions, please let us know in the comments, and in our future videos we'll continue working with these and explaining these things. Please let us know if these videos have been helping you. If you could help us out with a like or a subscribe so that you can continue getting notifications whenever we release a new video, that would mean so much to us. All right, thank you for sticking with me through all of that, and happy physicsing, y'all.